Welcome back, everyone. Hope you all had a good weekend. So let's continue our discussion on SVMs in CMPT 726 machine learning. So last time we talked about weak duality. In particular, we constructed the generalized Lagrangian function, and we can remember how that works by thinking of penalizing constraint violation. Taking the penalization into the extreme, where any constraint violation makes the objective go up to infinity, we wrote down the primal optimization problem as well as the dual optimization problem. And then we said that in general, there would be a duality gap, which is P star minus D star, where P star is the optimal value to the primal optimization, and D star is the optimal value of the dual optimization problem. So all of this discussion on weak duality was based on kind of the general constraint optimization problem. We then specialized to the SVM optimization problem, and then we derived the SVM dual problem. And this was again done by writing down the generalized Lagrangian and the dual problem. And for the SVM case, we actually did some simplification by solving the inner optimization. And after we did that, this is the result we got. So the primal problem was, for now, more straightforward to interpret. We want to minimize over W and B, which represent the decision boundary. And this objective was equivalent to maximizing the margin. We're subject to yi times W transpose xi minus b greater than or equal to 1 for all data points. This just means that each data point must lie on either side of the decision boundary. So this was the primal problem. After a lot of simplification, we derived a dual problem, which is maximized over lambda of sum of lambda I minus 1/2 double sum of lambda I, lambda j, yi, yj, xj transpose xi, subject to sum of lambda I, yi equals to 0, and also all of the lambda i's must equal to 0. So that was a dual problem. In general, there's going to be a duality gap, meaning that solving the primal problem will give us a value that is going to be greater than or equal to the value of this maximum. So today we're going to show that in the case of SVMs, strong duality holds, meaning that there's actually no difference between the optimal value here and the optimal value here. So we're going to talk about the Lagrangian duality. So the theory here is very deep. We're just going to kind of touch on some of the most important aspects. So let's talk about Slater's condition. So Slater's condition is a sufficient condition for strong duality to hold. It basically says that for a general optimization problem, if the objective f and all of the inequality constraints gi are convex, and all of the equality constraints are linear, and there exists a point that is strictly feasible, meaning that when you plug in theta 0 into all the gi's, you get strictly less than 0, not just less than or equal to. And also, this theta at the same time satisfies the equality constraints, then strong duality holds. So the mathematical statement is kind of a mouthful, but what it really means is that if we have convex objective, convex inequality constraints, linear equality constraints, and a strictly feasible solution, meaning that for this particular feasible solution, you can wiggle it around and it would still satisfy the constraints. So that's what that is what's meant by strictly feasible. So if all four conditions are satisfied, so these are the Slater's conditions, then strong duality holds, meaning that there's no difference between solving the primal and the dual problem. So we're going to show that for the SVM optimization problem, the Slater's condition holds. So that means checking all four of these conditions. So for checking Slater's condition for SVM, I guess we just have to go through the four of them, right? So Slater's conditions. So first of all, convex objective. Second, convex inequality constraints. Third, linear equality constraints. And lastly, strictly feasible solution. So what this really means is that there exists a strictly feasible solution. So we're going to check all of these. So to do that, we need to first write down the primal form of the SVM. So primal SVM problem. So that was minimize over W and B of 1/2 W 2 norm of W squared, subject to yi W transpose xi minus b is greater than or equal to 1 for all I. Okay, so let's check 1. So this is what we need to check. So for 1, do we have a convex objective? Actually, if you look at this is the 2 norms, so that all norms are actually convex. But if we really want to show that, we can say 1/2 2 norm of W squared equals to 1/2 W transpose W, which equals to W transpose 1/2 times identity times W, right? I can always put in an identity. So now this looks like a quadratic form. So this is a quadratic form with 1/2 I, which equals to 1/2 0 0 1/2, right? So this is actually positive definite. 1/2 identity matrix is positive definite because all the eigenvalues are 1/2. So therefore, objective is convex. So we have checked the first condition. For the second condition, it's actually pretty easy to check. We just have to check that the constraint, the inequality constraints are strictly, are convex. So we can rewrite the inequality constraints to make everything less than or equal to 0 on the right hand side. So we've already done this, so let me just quickly write this down again. It's going to be 1 minus yi times W transpose xi minus b. This should always be less than or equal to 0. So we want to show that this is convex in both W and B. So then we just have to take the, I guess the simplest way to check this is to take the Hessian of this, function on the left hand side, and then if the Hessian is positive semi-definite, then the function would be convex. So let's do that. So we can take the gradient with respect to, so actually let's name this function. So let gi of W and B equals to 1 minus yi W transpose xi minus b. Okay, then we can first take the gradient of g. We can do just with respect to W first, I guess. So when we take the gradient with respect to W, the first and the last term, so the first term is 1 and the last term is minus yi minus times minus b. Both of those terms do not depend on W. The middle term is yi W transpose xi, so that one depends on W. but and then so it's a term that is linear in W, and the coefficient is just going to be minus yi xi. Okay. And now we can do the other gradient, which is with respect to b. So b is only involved in the last term, and the partial derivative is just going to be yi. So now let's look at all four terms for the Hessian. So the Hessian of g is written as partial squared gi over partial wb partial wb transpose. So this is going to be equal to partial squared partial squared over, so the first one is going to be 2 derivatives of w of gi. Second one will be also 2 partial derivatives, but then it's going to be with respect to b and then with respect to w transpose. Okay, and then the other order. The order doesn't matter actually. And finally, 2 derivatives both with respect to b. So let's just do that really quickly. So for the upper left block, we just have to look at partial gi partial w over here. And we can see that that doesn't actually depend on w at all. So we just have a zero matrix over here for the upper left. Okay, on the right side, we can kind of see that actually if you look at both of these, we have kind of made the same argument before, right? When we first take the gradient with respect to b, the result does not depend on w. And then when we first take the partial derivative with respect to w, the result doesn't depend on b. So we're just going to get both zeros over here. And you guys can go back and check the dimensions, but there should be a transpose here. Okay, so turns out that we don't need this one here. Okay. And lastly, when we take the partial derivative with respect to b twice, we also get 0. So actually this turns out to be a zero matrix, which is indeed going to be positive semi-definite. In fact, because the Hessian is 0 everywhere, this is actually a linear, this function is actually linear in w and b, which I guess we should have seen because 1 minus yi times w transpose xi minus b, right? W and b only enters the expression linearly, and linear functions are convex. In any case, we have shown property number 2. Okay, I guess we're going to move over here for property number 3. Property number 3 is automatically true. We have no equality constraints. Okay, so now we just need to show that the SVM problem has a strictly feasible solution. Okay, so for this one, we're not gonna go through a lot of complicated math. We're gonna be using our geometric interpretation. So recall that we have a while ago we picked a scale for the SVM problem, and we picked the scale to be such that the 2 norm of w is equal to 1 over m. And m was the margin. And also remember that for SVM, what we're going to do is we are given a bunch of data points which have different labels, plus or minus 1, right? Assuming that the data set is linearly separable, meaning that we are able to find a decision boundary that separates these 2 classes, we can kind of see that we can always, whatever line we pick will have some margin, right? If there exists a line that separates these 2 classes, then we can actually wiggle the line a little bit. Wiggling the line meaning changing w and b slightly, and the line would still be separating these 2 classes. Right, so the fact that given a linearly separable data set, we're always able to wiggle a line that separates the two classes. This is a geometric argument for there exists a strictly feasible solution. Remember that strictly feasible solution means that we can always find a W and B which satisfies the solution, and we're still for that W and B we can change them a little bit and they will still satisfy the constraints, right? So that's exactly what we have in the picture. Given some feasible W and B, which is represented by this line here, we should always be able to wiggle the line a little bit, i.e. change W and B a little bit, and the line should still satisfy, it should still separate the two classes, meaning it satisfies the constraints. Okay, so I guess the geometric argument is can wiggle a line that separates the classes to get another line that also separates classes. Okay, so then we have shown the last condition as well. So we have checked all four conditions of the Slater's conditions. So that means that strong duality holds. So therefore, strong duality holds. This means that we can choose to solve the primal or the dual problem, and that's supposed to be equivalent. Let's look at this again on the slides. So what we did was checking that the SVM primal problem satisfies the Slater's conditions: convex objective, convex inequality constraints, linear equality constraints, and strictly feasible solution. So let's start with the first one, convex objective. So here, hopefully now you have a pretty good intuition that 1/2 the 2 norm squared is actually going to be a convex function, right? So we showed that by converting the objective into a quadratic form with 1/2 I as the matrix, and 1/2 I has eigenvalues of 1/2 and 1/2. So the objective is strictly convex. Okay, so now convex inequality constraints. So we did some algebra with the computing the Hessian of this function, which we called G in the written notes. But I guess now looking at a second time, we can immediately see that this should be actually a linear constraint, just because W and B appear linearly in the expression, right? There's nothing like B squared or W squared or W times B, for example. Okay, so our constraint is actually linear, so therefore it is also convex. So this shows the second of Slater's conditions. Next, we need to show linear equality constraints. I guess nothing to show here because the SVM problem does not have any equality constraints. And lastly, we need to argue that in the SVM problem, there exists a strictly feasible solution. And we didn't really show this mathematically, we showed this geometrically by arguing that the constraint is basically saying that the distance of each training point to the hyperplane should be at least the margin, right? That was the meaning of the constraint. And we set the margin to be actually 1 over the 2 norm of W. So if the data set, if we assume that a data set is linearly separable, we can always make the margin small enough for the constraint to be strictly satisfied. Okay, so then that shows that the fourth of Slater's condition is also satisfied, and therefore we have strong duality, and therefore the equivalence of primal and dual problems. So this is written down mathematically over here. So we can either do min over theta, max over lambda, and nu of the generalized Lagrangian, which is the primal problem. It equals to P star. That is actually equal to D star, which is equal to the same thing with the max and the min flipped around. Okay, and a single solution, theta star, lambda star, nu star, would be optimal for both of the problems, both the primal and the dual problems. Okay, so in the case of SVMs, that means that instead of solving the original primal problem, we can actually solve this one, which we derived last time. Solving this problem will give us the optimal lambdas, so lambda star, and then it doesn't really give us directly the optimal primal variables theta star, but we can always derive that afterwards. So to find theta star, which is W star and B star, we can solve the primal problem. And actually we already did that last time by solving the inner optimization problem over here. Okay, so in this case, in the case of SVMs, we just need to solve the inner optimization problem given the optimal lambdas, right? So basically what we have is that the dual problem is this one. Yesterday we solved the inner part. After we solve the inner part, the result is actually a function of lambda and nu, right? So then we can basically maximize over lambda and nu. That would give us kind of that would give us the optimal dual variables lambda and nu. Actually, this optimization problem itself will give us the optimal lambda and nu. So basically, the only thing we have to do is to optimize the inside, which we already did. Okay, but we can look at it again. So the generalized Lagrangian with the lambda star plugged in is equal to the objective 1/2 2 norm squared of W plus summation of lambda I star times our constraint. Right, simplifying a little bit, we have 1/2 W transpose W plus this summation, which expands out these terms. Right, so I'm just gonna go through this pretty quickly because we have written this down last class, right? The only difference is that last class we just wrote lambda star, lambda I, but now all the lambda i's are going to be lambda I star. In order to minimize this, we're going to take the gradient with respect to W and B and set it to 0. For the gradient with respect to W, first we work with the quadratic form here, which is going to be 1/2 I plus I transpose W, and then minus, for the second part, the only term that depends on W is going to be the middle term, minus lambda star I, yi, W transpose X. This is actually a term linear in W, so the gradient would just be everything other than a W here. So that's going to be lambda I star, yi, xi. Okay, and then nothing else. Everything else goes to 0. They don't depend on W. So now we can just simplify a little bit. The two i's here cancel with the 2 in the denominator. And then we don't touch this, we don't touch the second part. Setting the gradient to 0, we can actually move the summation to the other side so that we have W star equals the sum of lambda I star, yi, xi. Okay, so this is exactly the same as what we did last time, but with the lambda star here. Okay, so next we're going to find B star. So for this one, we did not actually, we were not actually able to derive the optimal B last time. So today we're going to do it geometrically. To do this, we need to go back and visit the SVM formulation before we simplified it a lot. So remember, on this page, we were basically talking about maximizing the margin subject to the different classes being on different sides of the decision boundary. And then also kind of the margin, all of the data points should be away, should have a distance of at least a margin from the decision boundary. So that was this constraint here. Okay, and then eventually we kind of, after a few steps, everything simplified a little bit and things started to look like this, right? For yi equals to 1, so for the positive class, we had that all the data points must be greater than or equal to m times the 2 norm of w. And then for the negative class, w transpose xi minus b must be less than or equal to minus m times the 2 norm of w. Right, so that was after a few steps. And eventually we kind of said that because the scale of w and b doesn't matter, we can actually pick the 2 norm of w to be 1 over m, so that m equals 1 over the 2 norm of w. And then that was how the right hand side simplified to 1. Okay, so that's kind of a quick reminder of how we got here, right? So now coming back to the final optimization problem with the constraint that yi times w transpose xi minus b is greater than or equal to 1. Whenever we have equality, that means that particular data point xi is exactly on the margin, is exactly the distance between that point to the decision boundary is exactly equal to the margin. So that means that we can actually write down the last two expressions. Okay, so basically, sorry, maybe let me just repeat myself again to make it clear. In general, we have inequality, but equality, so equals to 1 for the positive classes, and also equals to 1 over here for the negative expression. For the negative classes means that those points xi are actually on the margin. They're exactly the same distance to the hyperplane as the margin, right? So that intuition is coming from going back to revisiting the previous formulation before we simplified everything down a lot. So using this interpretation, we can actually write down that if we look at the minimum of w transpose xi minus b over all the data points, that must be equal to 1. Because the data points with the minimum distance to the hyperplane must have a distance of exactly the margin. And similarly for the negative classes, we can write down, if we minimize over all of those, and we calculate minus w transpose xi plus b, well, that must be equal to 1. Because the negative example that is closest to the hyperplane must have a distance of exactly the margin. Right, same reasoning on both sides. Okay, so that was kind of a geometric interpretation from revisiting the steps in the formulation. Okay, so now it turns out that these two properties here will allow us to obtain the optimal w and b given the optimal lambda. Actually, the optimal w was already determined over here when we set the gradient of the Lagrangian with respect to w to 0. So w star was already given. So what we're really doing here is that given w star, we would like to determine b, and we can do that using these two equations. Okay, and so let's do that now. So basically, the geometric argument gave us that min over I, so minimizing over the data points only for the positive classes of w transpose x I minus b, that should be equal to 1. And that's because the data point that is closest to the hyperplane should have exactly the distance of the margin, right? Should have a distance of exactly the margin. Okay, and similar thing for the negative classes. So min over I of where yi equals minus 1 of w transpose xi actually we need a negative sign here, minus W transpose Xi plus B equals to 1, right? So we're going to simplify these a little bit. The first step, we're going to pull the B to the outside. So that the minimum is only applying to W transpose Xi. Because the B doesn't need to be inside the minimum. It does not depend on I. Okay, so that's the first step. Actually, I think that's all we need to do for now on this side. So let's work on the other side. So again, we're going to first take out the B. Yi equals minus 1 of minus W transpose Xi plus B. That equals to 1. And then now we're going to use the property that the min of a function f of x is actually equal to the max, the negative max of negative f of x. Okay, so you can kind of see that if we have some function f of x, the minimum value is always equal to negative. So it's always going to be take minus f of x. So this would be min of f of x, right? So now at the bottom we have minus f of x. So this one would be max of the minus of f of x. And if you take the minus of that, you will get back min of f of x, right? So this, we're going to use this property to turn this min into a max. So it's going to be minus the max of minus the inside. They're going to be the same, so we can replace them. So we still have the plus b equals to 1. Okay, basically all we need to do now is just to isolate b. So we're going to take this, subtract this one. So let's just write that down. Max over I of yi equals to minus 1 of W transpose Xi plus B. So basically, I guess the point here is that we just want to somehow just isolate B using these two equations. Okay, I guess there isn't going to be anything too clever in here. So we're just going to minus the left equation. So min over I, where yi equals to 1 of W transpose Xi minus B. And that equals to 0 because they both equal to 1. 1 minus 1 equals to 0. Okay, and then we need a bracket here just to make sure that we don't make a mistake. So now we can just do some simple math, right? A lot of stuff to write, but the idea is pretty simple. Yeah, the first one is yi equals to minus 1 of W transpose Xi. So nothing changes here. Plus B minus, I'm just going to do the minus, multiply the minus inside here. Okay, so now it's good that we have 2b. So we have 2b on one side. So I'm just going to write a b, well, there over 2 here, but I'm going to divide by 2 at the end. And then I move the max and the min onto the other side. So it's going to be max of W transpose Xi. So the maximum is over I such that yi equals to minus 1, plus min over I such that yi equals to 1 of W transpose Xi. And then if we want to get rid of the 2 here, we'll just do it over 2, all of that over 2. So what we have derived is actually true for any W. right? So no matter what hyperplane we have, so no matter what direction the hyperplane is, so no matter what W, what we started off with, the geometric interpretation will always be true. The points that are closest to the hyperplane will be exactly a distance equal to, will have exactly a distance equal to the margin, right? So that's always true for any hyperplane. In particular, it's going to be true for the optimal W, which we have already obtained. So B star would just be the same expression, but you have to plug in W star. So taking a look at this again, so we began with the geometric interpretation, which was copied from the previous slide over here. With some simple algebra, I think that actually these two lines are identical, so we don't need to look at them both. So we just did one step to move the B outside. And then for the right-hand side, for the right column here, we also moved the B out and then used the fact that the minimum of some function is equal to the negative maximum of negative of the function. Right, so it's a mouthful, but hopefully you get the idea from the drawing I did. So the negative max of W transpose Xi plus B equals to 1. We take this equation, subtract this equation, and we get 0 on the right-hand side, 1 minus 1. And then in here, we just have negative max of W transpose Xi plus B minus min of W transpose Xi minus B. We kind of multiplied the negative sign in, combined the B together to have 2B, and then we isolated B, and this is what we got. So this expression is true for any W, and in particular, it's going to be true for the optimal W. So now we have obtained B star equals this expression, which is a function of W star. And just to remind you, this was actually a long process of, first of all, showing strong duality, right? Actually, first of all, deriving the dual problem of the SVM. That being this one over here. And then after we showed that strong duality holds, we realized that, okay, we can actually solve the dual problem first, and then solve the primal problem. Solving the dual problem would give us lambda star, but then solving the primal problem can give us our optimal weights. And that was actually done by first obtaining W star as a function of lambda star. And then after having obtained W star, we can now get B star. Now let's compare the primal and the dual problems of SVM a little bit. So if you look at the primal problem, the number of variables is actually little n plus 1, where n is the number of, the n is the dimensionality of W. So for example, if the data point, so W, remember W has the same number of dimensions as the data points X. So actually n is just the dimensionality of each data point. So the optimization here is over little n plus 1 variables. The dual problem is actually optimizing over big N variables, because lambda has the number of lambda variables is actually equal to capital N, right? So the dual problem is optimizing over big N variables. Primal problem is optimizing over, roughly speaking, little n variables. So whenever little n is much less than big N, then it's actually more efficient to solve the primal problem. Otherwise, if big N is less than little n, then it's actually going to be more efficient, at least have fewer variables in the dual problem. So that's basically from a purely computational perspective, right? Looking at small n versus big N. Actually, it turns out that there's actually another mathematical reason to solve the dual problem. I guess we'll start talking about it next. So when strong duality holds, and we know that it holds for the SVM problem, the optimal solution to both the primal and dual problems satisfies the KKT conditions. So KKT conditions actually are pretty straightforward, even though they look a little bit ugly here. So KKT conditions say that our primal variables must satisfy the constraints. So that's gi of theta star less than or equal to 0, and hi of theta star equals to 0, right? So this is just saying our solution satisfies the primal constraint. So these two conditions are called primal feasibility. We also have that lambda I star must be greater than or equal to 0. So this is dual feasibility. Remember, in our dual problem, we needed lambda I to be greater than or equal to 0. Right? So all this is saying is that both the primal and dual problems satisfy the constraints. Next, we have stationarity, which says that the generalized Lagrangian function must evaluate to 0 when we take its gradient. Okay, so basically this is partial f partial theta plus this sum with partial gi partial theta, and then plus this sum with partial hi partial theta, right? So this whole thing is just a gradient with respect to theta of the generalized Lagrangian. When we plug in the optimal solution, lambda star, theta star, and nu star, we should actually get 0. And finally, the last condition is complementary slackness, which says for all I, lambda I, gi of the optimal theta must be 0. So I'm not really going to derive these conditions or kind of explain too much about them. I'm just going to state that these conditions are indeed satisfied when strong duality holds. And then we're going to be focusing on the last condition and use that to interpret the solution to the SVM problem. Okay, so complementary slackness says that lambda I star times gi of theta star equals to 0 for all I. So that means that if lambda I is greater than 0, strictly greater than 0, that means that gi of theta star must be equal to 0. But because they multiply together to be 0. So in other words, if the dual variable for an inequality constraint is positive, the constraint must be an equality. On the other hand, if a constraint, so if gi of theta star is strictly less than 0, that must mean that lambda I star must be equal to 0, right? So in other words, if an inequality constraint is strict, then its corresponding dual variable must be 0. Okay, so the implication is always starting from one of these factors being non-zero, right? So when lambda I is greater than 0, that implies the other factor must be 0. And if the other factor is not 0, i.e. negative, then the first variable must be equal to 0. So the other implication, direction doesn't really hold. And that's because if one of them is 0, then the other factor could be 0 or non-zero, and for the entire thing to be 0. So now we're going to apply this to SVMs. So here I write down the primal and the dual SVM problems again. And for complementary slackness, this is a condition. Again, lambda star I, gi of theta star equals to 0. So for SVM, we have seen many times that our gi of theta is going to be this equation written in the form of something less than or equal to 0. So gi of theta star actually equals to 1 minus yi w star transpose xi minus b star. Okay, I'll give you a moment to kind of map everything in your head. So what exactly is this saying? So it turns out that this is saying that training data points whose dual variables are positive must lie on the margin. And training data points outside the margin must have 0 dual variables. Okay, so let's kind of break this down a little bit. Let's look at the first point. So training data points whose dual variables are positive. So that means for all the positive lambda i's, we must have that gi of theta star equal to 0, right? So that means that this expression is strictly equal to 0. That means that these data points must lie on the margin. So that's actually a direct translation of this mathematical statement. Okay, and then if you look here, remember that we derived W in terms of the summation of lambda I, yi, xi, right? So for any data points that lie on the margin, we have dual variables that are positive. And for any training data points outside the margin, we must have 0 dual variables. So that is actually the other statement. So training data points outside the margin, meaning that gi of theta star is strictly less than 0. For those data points, we must have lambda I equals to 0. So now looking here again. So for any data point on the margin, so let's take a look. For data points where dual variables are positive, so that means for any lambda I that is positive, these data points must lie on the margin. And then for those data points outside the margin, lambda I must be 0, right? So I guess the first thing you note is that any data points that are not on the margin, they will actually have a lambda I that is equal to 0, meaning that they do not contribute to this summation. And therefore, they do not affect W star, and therefore they do not affect B star. So all of these other data points over here, the ones not on the margin, they do not affect the decision boundary. On the other hand, when lambda I is greater than 0, meaning that for any data points that do affect the decision boundary, they must lie on the margin. Okay, so this is exactly what we expected from the geometry earlier, right? And now that we have solved the entire optimization problem, we see that the math says the same thing as well. Again, these data points, which are on the margin, i.e. they have non-zero lambda, they're called support vectors. Okay, and then again, by complementary slackness, they must lie on the margin. So support vectors must lie on the margin. So data points outside of the margin, they're not support vectors. They do not affect the margin or the hyperplane. Okay, so far we have been talking about kind of using a hyperplane, a linear hyperplane, to separate out the two classes. But sometimes the dataset may not be linearly separable, yet the dataset could actually be separated by using a curve, right? For example, this one. So this leads us to features. So remember in linear regression, even though our model was linear in W, we could still actually have a model that is nonlinear in the data points. So it's going to be the same idea here. We can actually introduce nonlinear features to our data points and then train an SVM to make the decision boundary nonlinear that way. Just to recap a little bit, some example features are the polynomial feature up to degree 2. So we kind of have looked at this before. So for this particular feature, we have the degree 0 term, which is 1, the degree 1 term, which is all the components of the vector x, and then all the degree 2 terms, including the cross terms. So the idea is that we should first change xi into phi of xi, and now phi of xi become the features, they kind of become the input to SVM. The primal problem would basically look the same, except that xi is replaced with phi of xi, and same with the dual problem. The dual problem would have xj and xi replaced with phi of xj and phi of xi. So this does not really change the dependency of the it doesn't really change how the entire objective as well as the constraint, what kind of functions they are of W and B and of lambda, right? They only change what is known, which is the data points. So they do not make the optimization problems any more difficult. So far, this is actually exactly the same idea as what we saw with features in regression. So it turns out that for SVMs, using features is not is actually a little bit more interesting than simply replacing x with phi of x. And we're going to be looking at that next after a 10-minute break. So we'll see you back in here after 10 minutes. Okay, let's get started again. So usually when we replace x with phi of x, very often we want to pick phi to have a much higher dimensionality than x. So for example, for the polynomial, our input, at least in the coding example with linear regression, our x was just a scalar, but our phi of x was actually 1x, x squared, x cubed, and so on. So phi was actually 1 plus, phi had a dimension that is 1 plus the degree of the polynomial. So you can kind of see that that was one example where phi had a higher dimensionality compared to x, right? So this is pretty common. So when we replace x with phi of x, computations actually get more expensive because this inner product becomes more expensive to compute. However, it turns out that we can actually compute phi of xj transpose phi of xi without actually explicitly computing the feature phi of xi. So this is actually much more efficient and is known as the kernel trick. So we're going to motivate this by looking at this example here. So let's suppose we pick the following feature, which is kind of similar to a polynomial degree, a polynomial feature up to degree 2. So yeah, let me write this better. Phi of x. So I guess I should put a vector on top of phi, but I think it's usually kind of understood that phi would be a vector. So let's suppose that phi is just going to be 1. So here we have that's the degree 0 term, and then we have a bunch of degree 1 terms all the way up to xn, right? So x is a vector of little n components. Here we're going to modify the feature to have root 2 as the coefficient on the terms. Okay, and then we get all the quadratic terms. So degree 2 terms, we have x1 squared, we have x1, x2, so we get all of these combinations all the way to x1, xn. And then we kind of proceed with x2 squared and so on, right? And then x2, x3, all the way up to xn squared. And then we're going to put a root 2 coefficient on all of these. So the coefficient doesn't really change anything, the fact that phi of x is the feature of polynomials up to degree 2, but it's going to be useful for us to have this root 2. Actually, we will not have the root 2 on the square terms, just the cross terms. Okay, so this is going to be our feature. So normally, if you choose this feature, you will see that the dimensionality of the feature is much greater than the dimensionality of the original input x. So that when we compute this inner product, which appears in the SVM problem, it looks like the computational complexity is going to be higher, right? But let's do a bit of math and simplify things a bit. So when we do this inner product, we're basically going to multiply each of the components in phi of x and phi of y together. So the first term is going to be 1 times 1, and then it's going to be plus root 2 x1, root 2 y1, and then plus root 2 x2, root 2 y2. So we can write this more compactly. And it's going to be sum from I equals to 1 to n of root 2 xi, root 2 yi. And that takes care of everything in the linear term. Okay, and then we can actually, for the quadratic term, we would have a double sum of xi equals to 1 to n, and then and then sum from j equals I plus 1 to n of root 2 xi xj, root 2 yi yj. Okay, so where does that come from? Basically, the xi, is basically coming from the fact that we need to multiply the different components of x itself together, right? So we have x1, x2, x1, x3, all the way up to x1, xn. And then we start with x2, x2 squared, x2, x3, and so on. And then there's also this term. So all of these, so this double sum is actually taking care of all the cross terms. And then we still need to have one term, one summation for the squared terms. So it's going to be sum from I equals to 1 to n of xi squared, yi squared. Okay, so that takes care of all the x1 squared, x2 squared terms. So let's simplify this a little bit. So first, we're just going to pull the root 2 out. And then we just have xi, yi. Next, we can, I guess, collect the square. So we're going to work on the last term first. I should have written that first, actually. So this is going to be xi, yi squared. And then finally, we're going to pull the 2 out. It's going to be 2 times this double sum. And then we're going to have all the xi, yi. So we're going to group them this way. So all 4 factors here, xi, yi, and then xj, yj. So it turns out that this is actually equal to 1 plus the summation of from I equals to 1 to n of xi, yi, all of that squared. So you can see that because we have the 1. When you square this whole thing out, you get the 1. And then you get the cross term where it's 2 times 1 times the summation. That gives us the cross term here. And finally, you have the second part squared. So then for the second part, this is actually all equal to sum from I equals to 1 to n of xi, yi, the whole thing squared. When you square this whole thing, you will get all the square terms, which are going to be xi, yi all squared. So the square terms, so the non-cross terms are going to give us this part. And then you're going to have all the cross terms, which will give us the second part. Okay, so I think it'll take a bit more work to work this out, but hopefully you can see this. If you don't see it, you can feel free to kind of expand out this this square, and you should be able to obtain all of the cross terms. Okay, so now we're going to continue with the main line here. So this simplifies to 1 plus x 1 plus x vector transpose y. And then all that squared. And then this is going to be defined to be what we call k, a function k of x and y. So basically what we have done with this math is that originally we had to compute this inner product, which require adding a lot more than just n terms. But it turns out that after simplification, we actually got something here which only required adding up about n terms, right? This is just x transpose y, and then you have to square that. Add 1 and then square the whole thing. So that doesn't take as much work as doing phi of x transpose phi of y. Okay, so this is an example of a kernel trick for the polynomial feature of up to degree 2. So coming back to the slides, let's look at it again. So we're going to choose a variant of the polynomial features up to degree 2. The variant is that we have the coefficients root 2 on everything except for the constant term and for the square terms. So now in SVM, the term phi xj transpose phi xi appears a lot. So we're going to compute in general phi of x transpose phi of y. And that is going to be just multiplying, kind of having writing down phi of x, phi of y, and then doing their inner product. So we're going to have the 1, and then we'll have all the linear terms multiplied together. So that's going to give us root 2xi, root 2yi added together. And then we have all the square terms added together. So that's sum of xi squared, yi squared, and then all the cross terms added together. So we have x1, x2, x1, x3, all the way up to x1, xn, and then we have the x2, x3, all the way up to x2, xn. So that's why we have the double sum from I equals to 1 to n, and then j equals to I plus 1 to n. And then we write down kind of all the terms in here. So if we have the xi xj and yi yj with the root 2 coefficient on each of them. Okay, so the next line looks like the same thing, so we don't need, okay, so that's the same line, so we're gonna come down here. So now just taking the root 2's out, leaving, kind of combining the squares into a single square, taking the root 2 out, and then reordering the factors in here. So we're gonna group xi yi with xj yj. And finally, all of this factors into a nice square. So 1 plus sum of xi yi, all of that squared. And again, to see this, we have 1 squared is 1. 2 times 1 times sum of xi yi gives us this term. And then afterwards, we just have this summation squared. When you square a big sum, we basically have to imagine having 2 big brackets next to each other. And then we simply multiply all the terms together. So we have the first term in the first bracket multiplied by each one of the terms in the other bracket. So that basically gives us a square term plus all the cross terms. Right? The cross terms are going to be basically x1, y1 times x2, y2, and then x1, y1 times x3, y3, and so on. So again, if you don't see this immediately, you can definitely write everything out, and you should be able to figure this out pretty quickly. So after this big square, we can simplify it further by noting that this is just a x transpose y. And the final result is something that is much easier to compute compared to phi of x transpose phi of y. And we call the final result k of x comma y, where k stands for kernel. So it turns out that even though adding features gives us the ability to have a model that is nonlinear in the raw input, but at a cost of higher dimensionality of the feature, usually, right? But despite that, it turns out that we don't really pay much of a computational cost due to the kernel trick. So k of xy is called a kernel function or just kernel, and there are many different possible kernels. So choosing features is actually equivalent to choosing kernels. So computing the kernel avoids directly computing the features, which can be very high dimensional and inefficient or even intractable. Right? Sometimes it does become intractable. Actually, kernels can allow us to use infinite dimensional features, meaning that our feature vector could have infinitely many elements. Yet computing phi of x transpose phi of y will only boil down to a finite computation. Okay, so the kernels are actually very, very useful. And actually kernels don't just apply to SVMs, right? The kernel trick can be seen in many different applications other than SVMs. So some common kernels. So the linear kernel is just x transpose y. The linear kernel is actually just the same as saying that we don't, the feature is the same as the raw input, so we don't really have a feature. We have seen the quadratic kernel, which is 1 plus x transpose y squared. So that is equivalent to choosing this particular feature here. Right? So the point is that choosing kernel is equivalent to choosing feature. in general, kind of to generalize this square kernel, we have a polynomial kernel. And this is just simply changing the 2 to the power of 2 to the power of d. So choosing this kernel is the same as choosing a feature where the term, where the elements of the feature is the term in a binomial expansion of 1 plus x1 all the way to plus xn, all of that to the power of d. And then we need to adjust the coefficients a little bit with some square roots to make things work out. So I'm not gonna write everything in detail here, right? Writing this even for the quadratic feature, it's much more complicated to write the feature compared to writing the kernel. It's going to be even more convenient comparatively when we use the kernel for a polynomial kernel rather than the polynomial feature. And finally, a very common feature is called the radial basis function kernel. So this kernel is actually equal to exponential of -1/2 x minus y 2 norm squared. So this is pretty easy to compute, but it turns out that the feature itself is actually an infinite dimensional vector. So it's actually the concatenation of an infinite number of vectors whose dimensions are the terms in the binomial expansion x1 plus until xn to the power of I. And then there's some adjustments with square roots. And then the coefficient is also very complicated as well. So we're not going to derive this, but this is a very common kernel to choose. And it actually represents, it corresponds to a feature of infinite dimensions. So again, choosing kernel is equivalent to choosing a feature. But the way we think about kernels can be slightly different and perhaps even more interpretable. So when we choose a kernel, basically we're thinking about the relationship between any two data points x and y, and we're basically creating a formula that tells us which x and y's are more similar and which x and y's are more different. So going back to the linear kernel, we know that in the original feature space, x and y's, which are pointing in different directions, are considered kind of different. And the x and y's, which are in the same direction in some sense, are more similar, right? So that is kind of reflected in a linear kernel where we're taking the inner product x transpose y. So when you have x transpose y being very negative, for example, then the two data points are very different, far apart. When x and y when x is equal to y, then we simply have the 2 norm of x, which is a positive number, right? So you can kind of see we do have some intuition about what kernels, what happens when two similar data points, like what the kernel will evaluate to when the two data points are close together, and what the kernel might evaluate to when the data points are far apart. So for the radial basis kernel, for example, we can see that when x is equal to y, we simply have exponential of -0 here. So the kernel equals to 1. So for the exact same vector, the kernel equals to 1. And for any vectors that are very, very far apart, the value of the kernel becomes smaller. So we can kind of have a different interpretation of how we compare two different data points when we use kernels. Okay, so now coming back to kernels in SVMs. So let's take a look at the SVM dual problem, which is maximize over lambda of sum of lambda. Right? So now with the dual, the sum is going to be over the number of data points, and then -1/2 sum over the data points, and a double sum actually of lambda I, lambda j, yi, yj, and then it used to be xj transpose xi here. But now with features, we have phi of xj transpose phi of xi. Okay, and then we were subject to, I guess I'll just write the abbreviation, subject to sum of lambda I yi equals to 0, and also phi of lambda I greater than or equal to 0 for all I. So we kind of said that the phi xj transpose phi of xi, that was kind of an expensive computation, but with the kernel trick, we can just actually write this as xj, k of xj comma k of xi. So we can either choose a feature and then write down and then kind of write directly the kernel in here, or we can simply just directly choose the kernel. Okay, so then kind of we can replace the phi, kind of the inner products involving phi with just a kernel function. Okay, so this is kind of about training, right? This is about finding the optimal parameters. So now we can kind of solve this optimization. So after we solve the optimization, we still need to do testing. So the way we do testing is going to be y hat test equals, so there can only be two options, plus or minus 1. And then we decide that by looking at, I guess, the optimal W that we get, right? So W star transpose phi of x test minus B star greater than 0. So after we obtain W star and B star, we basically have to evaluate a feature of a test sample, and then we basically evaluate W transpose phi of x test minus B star to see if that is greater than or equal to 0. If that is greater than 0, that means that that data point lies on one side, the positive side of the hyperplane. Otherwise, it would lie on the negative side of the hyperplane when this quantity evaluates to negative. Okay, so I'm going to simplify things a little bit and define this to be, it's still going to be plus or minus 1, but I'm just going to say this is just some test function, g test. So if you want to test whether a sample is positive or negative, we simply plug that data point into g. Okay, of course, where g is just equal to what we had before, right? So W star transpose phi of x test minus B star. Okay, so how do we, so this is kind of the final result, but how do we calculate this? We need to actually first compute W star. And W star equals to sum from I equals to 1 to big N of lambda I star. So lambda I star, we get it from solving the dual problem, yi. And it used to be xi before we used features, and now it's going to be phi of xi. And then B, so after we get W star, we can get B star, which is going to be max over all the data points, all the negative data points first, actually, of W star transpose. Let me rewrite that. W star transpose phi of xi plus min over all the data points, all the positive data points of W star transpose phi of xi. And then all of that over 2. So basically, so now the computation of W star and B star actually involves the feature phi, right? So So we need to do a bit more work to make the computation of W and B star simpler, to not actually require evaluating the features. So let's take a look at this. So we're gonna go back to G test. So G of X test. So this is equal to W star transpose phi of X test minus B star. And we're just gonna plug the expression for W star and B star in. So this is gonna be sum of I equals to 1 to big N of lambda I star yi phi of xi. Okay, so all of this is our W star transpose times phi of X test. Okay, minus B star. So now let's simplify a little bit. We're just gonna bring the phi of X test into the sum, and then apply the transpose. The only vector inside the sum is going to be phi, so the transpose also goes in. So this becomes sum of lambda I star yi phi of xi transpose phi of X test, and then minus B on the outside. And now we can replace this with k of xi comma X test. So at least for the part with W star, we don't ever need to explicitly compute or evaluate phi. We can always simply evaluate the kernel. So now let's see what's happening with B. So now we're going to look at this expression for B over here, and then we're going to plug in W star. And hopefully you can already see that once we plug in W star, we're going to get a phi transpose phi, and that will be the kernel, right? So, well, let's just write it down. So where B star equals to, again, max over the negative examples of, so writing down W star here. So W star is equal to sum of lambda I star yi and then phi of xi, and then we're going to apply the transpose right away here. So that gives us W star transpose, and then we multiply by phi of xi. So this is where it's important to get the indices and the summation correct. So before we had W star equals a summation over the index I, but this index variable can be anything. In here, because we have another index I on the outside for the maximum, let's change the index of the summation to a j without changing the meaning. Okay, so all of these are index j. Plus min over the positive data points, yi equals to 1, of sum over j equals to 1, lambda j star yj, and phi of xj. Transpose, and then multiply by phi of xi. All of this over 2. And here again we can see that the only way that phi appears in the expression is in the form of an inner product. So we can always replace the phi transpose phi with a kernel. So in this case, this is going to be k of xj comma xi, and then over here we also have k of xj and xi. So we never have to explicitly evaluate the feature or the inner product between features. We only have to evaluate the kernel, which is much, much more efficient. So let's revisit everything on the slides again. So here we're going to solve the dual problem to obtain the vector lambda. In the dual problem, if we simply replaced x with phi of x, then we would have this inner product involving potentially very high dimensional features. Fortunately, we can always replace phi transpose phi with the kernel, which is going to be much more computationally efficient. After we obtain lambda star, we can then use it to compute w star and b star so that we can do testing. And when we do testing, we basically plug in a test point into the function g, which is defined to be w star transpose phi of x test minus b star. If this test function evaluates to positive, then we predict positive for the label. And if the test function evaluates negative, then we predict negative for the label. In these expressions, we still see some phi of x's, which means that we may have to evaluate. So if we don't get rid of these, we still have to evaluate potentially high dimensional features. But after some work, first on the test function, where we replace w star with the expression for w star right here. So we're going to plug this into here. We see that we see that everywhere where phi appears, we get phi transpose phi. So in this case, phi of xi transpose phi of x test. So we can replace this with the kernel function. This is going to be much more efficient. For the b star part, b star is equal to this expression here, over here with the w transpose phi. After plugging in w star in here, we also see that we always have phi transpose phi. So here, I guess on the slides, I was not careful with the indices, so this summation should have index j in both cases. But in the end, what we have is really that everywhere, both in the training as well in the testing, everywhere where we see phi, phi always appears as phi transpose phi. That means that we can replace all of that with the kernel. So we can train and test without ever having to directly compute the features. And this is actually why we might want to use the dual form. It basically makes using features very computationally efficient. It can even allow us to have infinite dimensional features. So that's because even during the training, we can use the kernel trick. This is not true with the primal problem, actually. You can kind of go back and look. So before we said that when the data dimension is much less than the number of data points, then and when the data is not linearly separable, then we can actually use a nonlinear kernel to implicitly replace the raw input with features. And when we do this, it's going to be much more convenient to use the dual. So originally we said that, okay, if little n is much less than big N, maybe primal would be more computationally efficient. But with the use of kernels, that argument is going to be weakened for the primal case. So usually we actually end up using the dual problem for SVMs to give us a nonlinear decision boundary. So we can take a look at some examples. So this is a raw data point, 3 examples of data sets here. With a linear SVM, which means no features, only the last set of data points is kind of separated reasonably well. The other two, we can already see that they're definitely not linearly separable. With the radio basis function kernel, which is, let me pull it up here. Okay, not here. Let me try to find, okay, over here. So with the radio basis function kernel, which is this one, we simply evaluate exponential of -1/2 x minus y to the norm squared. So this is basically saying that data points that are closer are going to be more similar. data points that are farther apart will be less similar, right? So applying that basis function or applying the radio basis function kernel, we actually get pretty good results for all three cases. We also get somewhat good results for the polynomial SVM. Actually, maybe not that good. But I guess the point here is to show the different decision boundaries, which are basically between kind of the blue and the white colors here. Okay, so different kernels will give you different decision boundaries. With a linear kernel, you only have linear decision boundaries, which makes it much harder to separate the data points. So before I kind of mentioned that choosing kernels is equivalent to choosing features, and kernels correspond to features. But can we actually come up with kernels without having to derive what features they correspond to? Meaning that we can only just think about a measure for the similarity between x and y, rather than what feature leads to that measure of similarity. So it turns out, yes, through Mercer's theorem, we can actually say that we can actually propose kernel functions without knowing what the features are. Mercer's theorem basically tells us kernel functions correspond to some choice of features without telling us what choice. So here's the theorem. So it says that a kernel function is valid meaning that it does correspond to a certain feature if and only if k is symmetric. So this one is kind of obvious, right? So when you swap the data points, the similarity between them should remain the same. So k should be symmetric. K of xy should be equal to k of yx for all xy. And two, for any input data, 1 to m, the Gram matrix, which is constructed by evaluating the kernel on every combination of pair of points. So this matrix should be positive semi-definite. So in practice, we basically take a bunch of data points, we evaluate the kernel on every pair of data points, and we just make sure that the resulting matrix is positive semi-definite. So this makes the kernel trick even cooler, in my opinion, just because we can directly think about kernels. We never even have to directly think about the features. And as long as we use Mercer's theorem to make sure that the kernel is valid, we know that this kernel will correspond to some choice of feature. We don't even need to know what choice of feature. I kind of began mentioning this a little bit in a few slides ago, but basically kernels, the idea of kernels applies more generally beyond the context of SVMs. So it turns out that there are other methods where when we write down the optimization problem, the problem only depends on the inner product between the data points and not the data points themselves. And whenever this happens, we can always replace xi transpose xj with phi of xi transpose phi of xj. And then we can replace that with k of xi xj, which is going to be more computationally efficient. And this basically allows us to convert a linear model into a nonlinear model and still preserve the computational efficiency of the linear model. And this general process is called kernelization. So now we're going to look at a variant of SVM called soft margin SVM. So the idea is that sometimes the data points may not be linearly separable. So in this example, we have the red and blue classes. They're kind of mixed together and they're not linearly separable, right? Sometimes that could just be because the data points are just not linearly separable to begin with. Sometimes there could be some outliers in each class, which kind of messes up the data. And we still would like to find a decision boundary that will allow us to make predictions. So this is where soft margin SVM comes in. So the idea is that we're going to choose some separating hyperplane in black here. And the blue and the red are the plus and minus 1 plane for this hyperplane, right? So remember, hyperplane is when W transpose Xi evaluates to 0. So that's when evaluates to B, sorry. So W transpose Xi minus B would be 0 on the black line. on the red and blue lines, they're going to evaluate to 1 and -1. When you have some outliers, let's say this blue outlier, we're going to measure the distance between the blue point and the -1 plane, and that is going to be defined to be the margin CK or psi k. And similarly, we're going to measure the outlier red points from the +1 plane. So the red points are the negative examples. So we're going to measure them. We're going to compute kind of the degree of violation by measuring the distance between the outliers to the +1 plane, and that's going to be Cj for the red point. So the optimization problem becomes minimize 1/2 W square of the 2 norm of W plus a hyperparameter gamma times the sum of all of these violations. These violation variables are called slack variables. These CIs are called slack variables. And now we're subject to yi times W transpose xi minus b greater than or equal to 1. Right, let's just compare with the previous hard margin SVM, right? The normal SVM. So we required this greater than or equal to 1. Now we're gonna relax things a little bit. For every data point, we are going to allow some slack, Ci, and then all the Ci's are going to be greater than or equal to 0. So let's take a look at this and simplify. Let's simplify this optimization problem for the soft margin SVM. So let's write down the SVM Primal problem again, which is min over W and B of 1/2 2 norm squared, square 2 norm of W, subject to yi times W transpose xi minus b is greater than or equal to 1 for all I. So that was the vanilla or hard margin SVM. For the soft margin SVM, we're going to allow some violation, kind of some violation of the constraint. And the amount of violation is written as Ci. So this is called a slack, the slack. So slack variable. And then we're also subject to all the Ci's greater than or equal to 0 for all I. While we can't just allow constraint violations for free in some sense, so we need to penalize that by adding gamma times the sum of all the slacks. Okay, so let's try to simplify this a little bit. First, we're going to modify this constraint. So let's work on this constraint. And we're just going to say, we're going to move the C to the left-hand side. So it's just going to be greater than 1 minus yi W transpose xi minus b. And then the other constraint, I guess, is still going to be Ci greater than or equal to 0. Right, so this one would be here, unmodified. So when you combine these two together, on the one hand, Ci must be greater than or equal to this quantity. On the other hand, it must be greater than or equal to 0. So it must be greater than or equal to the maximum between those two. So we basically have Ci greater than max of 0 and 1 minus yi W transpose xi minus b. Okay, so now, let's collect everything again. So let's rewrite our optimization problem this way. So we have minimize 1/2 2 norm of w squared plus gamma times sum from 1 to big N of xi subject to xi greater than or equal to max of 0 and 1 minus yi w transpose xi minus b. If you stare at this a little bit, we're penalizing the sum of the ci's, which are all greater than or equal to this thing. So actually, we can just write the ci directly in the objective, right? So let's write that down. So that becomes min over w and b of 1/2 2 norm of w squared plus gamma, and then sum from I equals to 1 of max 0 1 minus yi w transpose xi minus b. Basically, we want to minimize this entire objective, meaning including minimizing this part, right? If we minimize that part, that is basically that is kind of the minimum slack we're allowed to give, basically, right? So at optimum, so if you look back over here, the optimal slacks are going to be equal. So if you have a slack that is too large, which is strictly greater than this max thing, then that's actually not optimal, right? For the optimal xi, you always want them to be exactly equal. You want them to be tight. So basically, you can think of this as equal at optimum. And therefore, we can simply move the xi greater than or equal to constraint into the objective. And that's actually equivalent. Okay, so now we have this optimization problem, which is unconstrained for the soft margin SVM. So we're going to do a bit more work to it. First of all, I can always divide the objective by gamma, because the constant in front doesn't really matter. And then I can name that 1/2 gamma lambda. So I think we should probably stop here. So next time we're gonna analyze a little more the difference between square loss and the hinge loss to kind of understand, to gain some more insight into what we're really doing with soft margin SVM. And don't worry, these terms will make sense next time. Okay, so I'll see you guys next time.